go live. I just want to admit the last two people who entered. So we're ready to start. Hello, everyone. I'm Maura Pinter, and I'm a postdoctoral researcher at the University of Cagliari. Today's event will be for today's event we invited Giulio Rossolini, who will shortly be introduced by Luca, and then who will give us his talk. Just a few things before we start. First of all, the event is live streamed and recorded, so if you don't want to be recorded, feel free to follow on YouTube. Then after and during the event, you can ask your questions to the speaker. We will prioritize, of course, the questions from the Zoom channel. So either raise your hand or also write in the chat. And then if there is time left, we will also check out the questions on YouTube. If you want to follow us and check our next events, you can either follow us on Twitter, LinkedIn, Eventbrite, or also through the website that I prepared that contains all the information you need for finding the next events. And Luca will paste the info in the chat very soon. And also, if you're interested in machine learning security, you can check in the same YouTube channel where we are giving our web live streaming. There is a course that is for free and available to everyone that we taught last year in the machine learning security course, and you can access it. And there is also a repository with the code and everything you need. Also, I want to mention that it's the first year that we did this seminar. So this is the first event of the second year. And I am extremely grateful to all the people that came as guests in the last year. I also found some of them around the world. When I met them, I asked them a picture. So this is just a summary of my experience as organizer of these seminars. And I also am very pleased to share some numbers on the seminars, on the last seminars. First of all, we have an increasing amounts of views thanks to the speakers and the very interesting material they are bringing to our series. And also we have coverage basically all around the world, and thank to all our followers and listeners. Lastly, I want to thank all the people who helped me organize these seminars. So thank you all. And now I'll give the stage to Luca, who will introduce our speaker for today.
Oh, okay. So Giulio Rossolini is a PhD student at the Department of Excellence in Robotics and AI and the Real-Time Systems Laboratory of the Scuola Superiore Sant'Anna of Pisa. His research topics include the design of robust tools and architectures to enhance the trustworthiness of deep learning models in computer vision applications and safety-critical systems. So, and today he's going to talk about on real world adversarial robustness against physically realizable attacks. So, Giulio, the stage is all yours.
Yes, can you hear me?
Yes.
Okay, thank you very much for the introduction and for the invitation. So can you see the screen?
Yes, it's slides full screen.
Okay, good. So the topic of this presentation, as you can see from the title, basically is a physical realizable attacks. I think many of you know what physical attack, physical patches, or physical realizable attack is in general. Let me just, okay. So we can say that shortly, it's a very short introduction of real-world adversarial attacks. And basically, we can say that physical realizable adversarial attacks or real-world adversarial objects are robust and universal objects, which are adversarial in the sense that they are crafted to fool the model prediction when tested in real-world scenarios. And these are just possible examples in the literature of paper that present new approaches for crafting adversarial patches or real-world adversarial attacks. Probably one of the most famous approaches, adversarial patch, where basically this approach allows to, let's say, craft adversarial patches which are robust to multiple transformations, rotations, different images, to correctly misclassify the image with respect to a given image classifier. And also there are other works in the literature, for instance, adversarial t-shirt to full person detection systems, also adversarial billboard to full depth estimation system. There are many works in the literature that present real-world adversarial attacks. So here, I've just an additional slide. This is just an introduction of real-world adversarial attack. And here I have a slide to just highlight the importance of real-world attacks in practice, especially when we are dealing with safety-critical systems, when we are dealing with the cyber-physical system. And there are many, let's say, discussions in the literature that question the practical feasibility of adversarial attacks, a common adversarial perturbation, common adversarial attack, especially from the attacker perspective. And this is because when we are dealing with a cyber physical system and we have that the input image is collected by a camera, for instance, an attacker, in order to inject the common adversarial perturbations, require first hacking the software security mechanism. And this task could be really challenging and also expensive. And another important point is that assuming that the attacker is able to hack all the software security mechanisms, I mean, it leaves room for more dangerous attacks. So he can also, let's say, introduce software attacks, use common software attacks instead of just using epsilon perturbation, adversarial perturbation, or he can just use unbounded perturbation. He can just put some pixels of the image to plus or minus infinity to misclassify everything. And let's say that with this observation, I don't want to, let's say that the adversarial perturbation are not important. Adversarial perturbation are very useful tool to evaluate the robustness of AI-based system, of deep learning system. But when we are dealing with the feasibility of the attack, especially in safety critical system, like an autonomous robot, an autonomous car, there are several questions about the feasibility actually. And for physical realizable attack, the story is different. In this case, the physical realizable attack are objects that are capable of injecting the adversarial noise, the adversarial features directly from the external environment. So they allow bypassing the software security mechanism of the safety critical of the cyber physical system. So to conclude this presentation, I have an additional slide to just remark a baseline for crafting adversarial patches. In particular, I think many of you know this optimization paradigm, which is the expectation over transformation, which is, let's say, the baseline for crafting adversarial patches. Here we have our adversarial patch, which is delta. And basically, with this optimization problem, we want to minimize the pixels of delta, the pixel of the adversarial patch. We want to, let's say, we want to find the best delta, the best adversarial patch that minimize the, let's say, an adversarial loss, which is a specific loss function, which depends on the computer vision task, the target computer vision task. And also we computed on the output of our model, which is our deep learning model is half here. And we have also a ground truth adversarial label, and which could be also the original ground truth, depending if you want to attack, want to perform a target or non-targeted attack. And basically here we want to minimize this loss function following an expectation. So it means that we want basically to produce an image agnostic adversarial patch or a universal adversarial patch among a large set of images. And we want also to make this adversarial patch robust against possible appearance or positional transformations, which could be scaling, rotation, or regarding the appearance, we can apply Gaussian noise, blur effect, or printability score. There are many possible transformations. So this is the main baseline for crafting adversarial patches. So this is the last slide of the introduction, and I can start discussing 3 different work about physical realizable attacks that we carried out in our lab. The first one is an extensive analysis on the adversarial effect of real-world adversarial attacks for semantic segmentation model. In particular, I would like to first introduce the main motivations of this work. And we noticed that there are a few works in the literature that address the real-world adversarial robustness of semantic segmentation model. Although there are many for image classification or object detection, there are few works in the literature that address semantic segmentation models. While semantic segmentation model, by definition, provide, as you know, provide an pixel-wise classification. And this pixel-wise classification, this output, let's say that automatically provides a better interpretation, visualization of the adversarial effect of, for instance, an adversarial patch. And we can better exploit this visualization to understand the spatial robustness of the model. With spatial robustness, I mean, we would like to better understand how much an adversarial patch, for instance, can spatially corrupt the output prediction. As you can see here, the adversarial patch basically corrupts all of this area of the image. And this is one of the main motivation that inspired us to perform this analysis. The second one is that there are few works in the literature that address the effect of adversarial patches in outdoor environment, especially in outdoor autonomous driving scenarios, where let's say that testing adversarial patches in the real world, especially in outdoor environment, could be really challenging and expensive. We will see in the next slide. So this is just an outline of our evaluation. Basically, what you can see here is the pipeline, is the scheme of the illustration of the pipeline that we use to craft adversarial patches, which is very similar to other pipeline used for crafting patches for object detection or image classification. So just we start from a set of images, and then we had the adversarial patches, 1 or 2 adversarial patches actually, using spatial transformation or projected transformation, depending on the optimization. I will show you 2 types of possible optimization approaches. In particular, one is the classical expectation over transformation. The second one is a new technique that we present in this work that we call SceneSpecific Attack. And basically, they provide the transformation used for correctly trained adversarial patch. And then we also use appearance transformation, as I said in the previous slide, as Gaussian noise, blur, and printability score. And once we get the patched images, we feed these images into the semantic segmentation models. We compute the predicted semantic segmentation, and we compare the predicted semantic segmentation with the ground truth, and through the loss function, we backpropagate everything to update the pixels of the adversarial patch. Now, in this outline, basically, we evaluate different attack approaches, in particular, as I said, 2 different optimization paradigms, and also we evaluate targeted and untargeted attacks. We also present as an important contribution of this analysis, we present a new approach for improving the optimization time, and also the adversary effect of possible adversarial patches in semantic segmentation that we call the weighted pixel-wise cross-entropy gradient. I will address this point in the next slide. And we perform all of these attack approaches in different evaluation scenarios, in particular on the digital world, which is the common practice, let's say, fortunately sometimes, with basically you put the adversarial patch on top of the image at pixel level. And then this is, let's say, the worst case scenario. But we also evaluate that these adversarial patches in simulated environments using the color simulator, we will see, and also in the real world. So in the outdoor scenarios out of our lab. So regarding the weighted, the improvements with respect to the baseline for crafting adversarial patches, I would like to introduce the approach step by step. And in particular, we can, let's say, in order to craft adversarial patches for semantic segmentation, we can start implementing the expectation over transformation paradigm, which is this formula, basically. And usually, a baseline for implementing this approach is to implement a projected gradient descent. So where here is this loss function is a pixel-wise cross-entropy computed among all of the image pixels. So it's the mean of the cross-entropy of all the image pixels. We compute the gradient of this loss with respect to the adversarial patch at time t, and then we update the pixels of the adversarial patch following the direction of this gradient. This is the common technique used for implementing the expectation over transformation among different images of a given dataset using different, let's say, appearance and positional transformation. Now, to improve this baseline, basically, we present a new approach, and we redefine at runtime the gradient of the loss functions. So here we are not redefining the loss functions. We are redefining the gradient of this loss function, where basically is the following. Basically, is a convex combination, let's say, of two different gradient of a pixel-wise cross-entropy, where these two different pixel-wise cross-entropy are computed on two different subsets of the image pixels. In particular, M is the subset of image pixels that are still correctly classified, while M bar are those pixels that are misclassified. And basically, using this approach, normalizing these two different gradients and using lambda to control the importance of the gradient of these two subsets, we can improve the training performance and also the adversarial effect of the adversarial patch. So the rationale of this approach is that we notice through different preliminary experiments that those pixels that are close to the adversarial patch usually have a gradient larger than all the other ones, the other ones that are far from the other patch. And since this model are high performance model, actually, we assume that the majority of pixels that is misclassified is mainly due to the adversarial patch. And so M bar basically, since it's those pixels that are misclassified, at the same time depicts also those pixels that are close to adversarial patch, while M are those pixels that are correctly classified, but also those that are far from the adversarial patch. So basically, using this approach, again, we are able to control the importance of each pixel during the patch optimization and let's say, increase the corrupted area through the adversarial patch. And it allows speeding up the optimization, as you can see here, through this plot where we compare the effect of the weighted pixel-wise cross-entropy gradient with respect the baseline using the pixel-wise cross-entropy computed on all the image pixels or all the image pixel without addressing the patch-wise pixels. And as you can see here, we improve the optimization time and also the adversarial effect of the patch. Okay, so moving on the experimental results, I didn't put the numerical evaluation here. You can find all the values, all the experimental results in our paper. I just put some illustration in this slide where that basically show the effect of possible adversarial patches in the digital world. So in this case, in this evaluation, we just put the adversarial patch on top of the image, and we compare the adversarial patch with respect to random patch. Actually, we tested 3 different patch sizes. This one is the medium one. And we can see here that the effect of adversarial patches is, let's say, depends on different factors, from different factors, actually. The first one is the model architecture. The architecture, for instance, using an architecture like PSP.NET, which has a high exploitation of the image context, we can see that they are really prone to possible adversarial, physically realizable adversarial attacks. While if we try to craft an adversarial patch for other models that are less, let's say, do not perform a particular exploitation of the image context, they are quite robust to possible adversarial attacks, as you can see here. We also perform our evaluation in the real world, and let's say in the real world, as I anticipated, is quite challenging because we, especially in the outdoor environment, we notice that the patch size is an important factor. And so we need to, let's say, print very large adversarial patches. This is just a very quick demo where we can see that we printed an adversarial patch for the ICNet model. And this is the 2 meters adversarial patch. And only once we are close enough to the adversarial patch, the camera is close enough to the adversarial patch, we can start noticing, start addressing a possible adversarial effect here of this patch. So the distance on the patch, actually the size of the patch is a really important factor that, let's say, determine the adversarial effect of this patch. Okay, so if you have any questions? Okay.
Maybe I have one, actually.
Yes, yes.
So you mentioned that different models might be affected by these patches in different ways. Did you also test transferability effect? Like,
yes.
For example, creating a patch with one model and trying that on the other model?
Yes, we performed this test actually in the supplementary material of this work. And the black box, let's say, the black box transferability, so training an adversarial patch on a specific model and then testing its effect on other models, we noticed that it's quite challenging. Sometimes, let's say, each patch follow specific patterns of each specific model. So the transferability, there is no transferability actually.
Yeah, I was wondering actually if there is, for example, one architecture that creates stronger attacks in the sense that maybe they transfer better. Yes.
Actually, we didn't notice that.
Okay, okay. Thank you.
Yeah, I mean, black box attacks is quite interesting, and so it is interesting for future work. Okay, if there are no other questions, I can move on. And this is the next optimization. I told you, as I said in the previous outline, we tested 2 different paradigms for optimizing adversarial patch. And the first one is the expectation over transformations. And in this case, we present a new approach. And this approach, we call this approach SceneSpecific Attack, where we assume a war scenario. We assume that the attacker, let's say, knows in advance how to place the adversarial patch in the target scenario. So basically, the adversarial patch has a fixed position in a specific scenarios, in an autonomous driving scenario, in a driving scenario. And in these settings, we can perform, let's say, a scene-specific attack, in the sense that we can revisit the expectation over transformation paradigm by just optimizing the adversarial patch among images and viewpoint of the specific scenario. Images in the sense that we just collect images of the target scenarios, and viewpoints means that we are just limiting the possible transformation that we use in the classical expectation over transformation. Instead of using rotations, random scaling, random positions, we want to, during optimization, during the digital optimization, put the adversarial pixels of the adversarial patch exactly in the same position of a reference billboard, as you can see here. And the main problems for crafting, for, let's say, implementing this approach is that we need, first of all, the ground truth annotations of each image. And also we need the patch projected matrices. So to correctly compute the projective transformation for mapping the digital adversarial patch to the reference billboard. And so to face this problem, we leverage the Kala simulator, and that basically provide an automatic procedure to place an adversarial mesh in the simulated environment to collect images from this environment, and also to collect annotations of all of these images, but also provide a way for automatically extracting the billboard pose and placement of each image from each image. And so then we use this pose to compute the projected transformation, so then, which then is used to correctly add the pixels of the adversarial patch on top of the image, but particularly overlapping the pixels of the reference billboard. We still use the appearance transformations, again Gaussian noise and blur and printability score. And then we use we follow the same pipeline of the previous approach. Another important thing is that we tested the effectiveness of these adversarial patches, let's say, through by importing the adversarial texture at the end of the optimization in Carla as new textures of the patch of the billboard meshes. And so that we can collect a new adversarial dataset and then test the adversarial effect on this dataset. It is a fair comparison because we directly test the effect of adversarial patch it's not a digital evaluation, but we tested the effect in the simulated environment. So it's not actually exactly real world, but we put the patch in the simulated environment. So this is just a quick demo that we have of our adversarial patch. And we can see here that as soon as the adversarial patch is close enough to the camera, basically there are several misclassified pixels. Some of them are also quite far from the adversarial patch. And we have also comparisons with other approaches and random patches. As you can see here, we compare the scene-specific patch with the expectation of a transformation or against random patches. And in particular, the scene-specific attack, let's say, outperforms the effect of classical expectation over transformations. Okay, so do you have questions?
Yeah, yes, Giulio, I'm
yes.
Fabio. I'm Fabio. I have a quick question. What is the explanation that you can provide about the effectiveness of scene-specific patch? Why is corrupting so much the result of semantic segmentation? Is this due to the particular loss function that you use, that you use the new formulation of the coupling, the gradient, with two components of the gradient is due to this? And so you consider more the effect on the pixels outside of the patch. So you are trying to corrupt more the part of the image outside of the scene-specific patch.
Let's say that regarding the scene-specific patch, I think that the main reason to explain why it is better than the classical expectation over transformation, honestly, is because we are actually, let's say, overfitting the adversarial effect of the patch in this specific scenario. While using expectation over transformation, you are actually improving the transferability of your adversarial patch now. Because probably the adversarial patch computed with the expectation over transformation maybe is not effective as the scene-specific patch in this specific scenario, but maybe it's more effective in other scenarios because you are actually using the expectation of transformation. You consider a larger data set, larger set of images, but moving if you want to assume a worst case scenarios, you want to attack a specific scenario, you are using the scene-specific attack, you are actually overfitting the effect of your adversarial patch in this scenario. I think this is the main reason of why the scene-specific scenario, scene-specific attack, is better than the expectation over transformation.
Okay, thank you.
You're welcome.
I have also a super fast question. Do you think you can somehow port the framework for also moving patches? Like imagine a drone that crosses the how can I say the scene somehow, or is it just or is just too complicated to plug these slight modification inside the framework?
You mean change the position of the adversarial patch in other?
In this moment, there is a projection matrix that basically encodes how you basically create the adversarial patches. What I was thinking is, can you draw some trajectory in 3D space, which is just not a scale of a matrix, and reuse all of the framework, but by being general enough on the trajectory that you want to trace inside your scene.
Okay, so so instead of using the projective transformations, you are
Exactly.
No, it's a good. It's a good point. No, in this case, we just for each image we compute the poses, the pose matrices, and then. But it's a good point. At least because one of the main future work that we present at the end, but it's good to point out now. Is that we would like to improve this, to transfer these scene-specific attacks to also real world, because actually with our approach, we can just test this scene-specific attack using Carla simulator or any possible autonomous driving simulator. So it's a good point, I think.
Okay.
And it's also possible, probably.
Okay. Thanks.
Thank you. Okay, so I can move on to the second part of this presentation, where here the topic is still, of course, to physical realizable attacks, but what we want to do is to implement a defense mechanism to, let's say, mitigate the effect of these adversarial patches or adversarial object in general. So we pose three requirements for implementing a defense approach, and basically the first one is that we want a defense mechanism that is still effective in the real world as for adversarial attacks, and you want also a defense mechanism that is lightweight and let's say it works at runtime. In particular, it's quite an industrial requirement that maybe it's worth addressing a defense mechanism with a computational cost that actually lower than the deep neural network inference, for instance. And also, since we are dealing with the safety critical system or cyber physical systems, it's worth addressing a defense mechanism that should be robust and deterministic. And to face all of these points, we let's say we started our investigation looking that adversarial patches are quite related to high overactivation behaviors in the internal network layers. And there are some works in the literature that try to prove that in order to, let's say, reduce the importance of all of the other features in the image out of the adversarial patch, the adversarial patch is somewhat constrained to, let's say, produce overactivations in order to corrupt all of the other features in the image, the internal model features. And so, following this approach, we basically, this is in the same analysis that show you in the previous slides. We basically implemented zeta score analysis for detecting adversarial patchings in a selected layer L. And the zeta score is computed using a channel-wise mean and standard deviation, where basically the mean and the standard deviation are computed on a data set of clear samples, so not attacked samples. And using the zeta score, we can extract an overactivation score through the sum of the zeta score activation above the n percentile. And we can see just in this illustration all the numerical results. We also tested this approach in the digital evaluation. But in the real world, this approach is effective also in the real world. As you can see here, we have the overactivation score in multiple frames of the previous demo. And basically, we can just compute a threshold using an RLC analysis and in order to detect possible adversarial patch. However, this approach is not perfect. As you can see here, frame 18, we have the adversarial patch start to produce an adversarial effect, and we still get a low overactivation that is below the pre-computed threshold. So in order to improve this analysis, we present a new work. And basically in this work, we still focus on the overactivation analysis, but we introduce a new problem. The problem is also masking physically realizable attacks in the real world in order to mitigate the effect of adversarial patches. And basically, we wanted to perform this task using only overactivation analysis, without introducing any additional masking mechanism based on convolutional neural network, which is, there are several works in the literature that try to mask adversarial patches using convolutional neural networks. However, it's a quite unpredictable approach. And so the main point is that how can we improve the previous work, the previous analysis, this score analysis, to correctly mask the adversarial patch. So we addressed two points basically to achieve this, to solve this problem. And the first one is that in this work we present a spatial zeta score analysis instead of a classical pixel-wide zeta score analysis. This is because a classical pixel-wide zeta score analysis provide a scarce and non-contiguous mask. So that's just supposed to select a layer and then perform a zeta score analysis. And we get an heat map if we compute the average between all of the channels. We compute an heat map, and then we can use this heat map using a threshold. We can just extract a mask. However, using a classical pixel-wide zeta score analysis, we have a not contiguous mask. And while instead using a spatial zeta score analysis, and that I will present this analysis in the next slide, we can get a more accurate mask that allows correctly masking the adversarial patch. The second point is that we perform a multi-layer overactivation analysis. In particular, we mix multiple analyses performed among different layers of the deep neural network. And the rationale of this approach is that we noticed through preliminary experiments that shallow layers of the deep network model generally contain high medium overactivations in the spatial image areas, while in deeper layers, for instance, bottleneck layers, such overactivation grow in magnitude. And so, in other words, we can see, as we can see from these images, basically here the adversarial patch has a high medium overactivation. However, there are also other artifacts in the image. So just using a threshold here, maybe it's not enough to correctly extract a proper adversarial mask. And so we can use an heat map computed in deeper layers to perform something like a spatial attention and just focus on a specific area of the image to then perform a threshold and extract a defense mask. So these are the two main blocks that we use to implement the two previous points. The first one is the spatial pooling refinement that basically implement a cascade pooling refinement. So using multiple pooling layers, average pooling layers with different kernel sizes, we just perform in a deterministic manner. We extract the adversarial, let's say, a proper heat map starting from a pixel-wise zeta score analysis. And basically, this cascade pooling refinement allows filtering out high noise in the zeta score heat map. And it's also a possible way of extracting a proper adversarial mask without introducing any additional learning component. Then this is the second block that we use to mix multiple heat maps extracted from different network levels. In particular, this block perform just two soft thresholding using, these are just 4 parameters. And basically the idea is that, again, we apply a first threshold to the heat map extracted from deeper layers. Then we perform a spatial attention. And then again, we use another threshold to correctly extract the adversarial mask. We also compute an overactivation score as in the previous work. And this overactivation score is used to, as let's say, a detection flag with respect to a threshold that basically allows, helps to decide if use or not the adversarial mask. So regarding the experimental results, we tested this approach in the digital world. I forgot to say that this approach basically is a task agnostic. So we can use these mechanisms on top of any convolutional neural networks. And so we tested this mechanism for object detection, for instance, on COCO, and on semantic segmentation, for instance, we use Cityscape. And we also tested the approach on real-world data set, such as Apricot, where we have real-world adversarial patches. As you can see here, the Z-mask produced this mask, the adversarial patch. We have also a very quick demo that we carried out in our lab, where basically here we can see that the defense mechanism masks the adversarial patch, which is actually very similar to a zebra. And here we have the monitoring of the internal layers over activations using the spatial analysis that I presented in the previous slide. So the last slide of this part of the presentation, I would just like to highlight two important experiments that we carried out in the paper. The first one is that we highlight the importance of the overactivation analysis when we are dealing with adversarial attacks. In particular, we highlight the relationship between the overactivations and the adversarial effect. And in particular, we presented a new expectation over transformation. Let's say we revisit the expectation over transformation to add an additional loss function, as which we call activation aware loss function. And basically, this loss function, let's say, depending on the value of beta, we this loss function take into account the overactivation value on the internal network layers produced by the adversarial patch. So using beta equal to E beta 1, we are performing the classical expectation over transformation. Our adversarial patch produce a clear adversarial effect and also get a high overactivation. However, using a smaller value of beta, we increase the importance of the overactivation. So we want to craft adversarial patch that has a lower activation in internal network layer. And we can see also that we are reducing at the same time the adversarial effect. So it means that there is a relationship, an important relationship with the overactivations and the adversarial effect. In the second part of our paper, we also test our approach against defense-aware attacks. So we tested the worst case scenario. And basically, we tested two different defense-aware attacks. One, again, we present this approach where here we use the loss function for attacking that takes into account our defense. And basically, in a first analysis, we propose a loss function that aims at reducing the IOU of the predicted mask of the defense mask with respect to ground truth. And instead, the other attack aims at fooling the detection flag. In both cases, we achieved very good results in the sense that we compared our approach with other ones that use convolutional neural networks. And basically, our approach is quite robust. And in particular, we defined that our approach is, let's say, we can provide an explainable robustness. Explainable robustness in the sense that we know in advance which are the main actions, which are the main steps that an attacker have to do in order to fool our defense. In particular, the attacker is required to reduce the overactivation in order to bypass our defense. And this is due to the high relationship between overactivation and adversarial effect again. And however, crafting adversarial patch with a low overactivation inevitably produce less effective attacks. So this is why we define this as an explainable robustness. Okay, so this is the end of this part of the presentation. Do you have any question?
So just one thing, since I think we're gonna be like a bit longer than expected, I would advise everybody to have questions either to post it on the Zoom, and we're gonna answer them all at the end, just to save some time now, go to the main topic, and then be back with questions. Okay, sorry.
Thank you very much. I will try to conclude this part quickly. So this is the last work that I would like to present. And in this work, basically, we leverage our previous analysis on Carla in order to, let's say, provide a tool for an automatic generation of photorealistic real-world scenarios, autonomous driving scenarios that could be useful for testing or, let's say, benchmarking the adversarial robustness of models or possible defenses. In particular, first of all, we improve the scenarios, the simulated scenarios, switching our tool to the Carla Town 10 HD, which is quite photorealistic. And the main idea of this paper is that it provides, again, an automatic generation of possible data sets that are fully configurable from the user. So the user can basically decide how to put an adversarial patch, the size of the adversarial patch, and can also decide other parameters important for collecting the images for training the adversarial patch or for training on defense mechanisms, for instance. And we also extend the number of computer vision tasks. Specifically, we tested our adversarial patch on semantic segmentation models, object detection, and also depth estimation, and also 3D object detection. And this is more or less the pipeline of this work. So how to extract data set with adversarial patches in driving scenarios, in simulated driving scenarios. Let's say that for each scenarios, we basically the HIGO vehicle of the cameras are spawned at different distances from the adversarial billboard. And also we randomize the NPC in Carla, so the vehicles and the pedestrians. So basically, again, we are performing a scene-specific attack, but we try to randomize the situation in that specific scenario. And so we provide several configuration files where the user can set all the parameters again to correctly extract specific scenario. So again, we use this approach to create a billboard dataset. Then we use this dataset that provides the ground truth, the images from Carla, and the pose matrices to perform a scene-specific attack. Then we run an adversarial patch. Then from the scene-specific attacks, we get the adversarial patch texture. We import this adversarial patch texture then in Carla again, and we apply this texture on top of the meshes of the reference billboard to finally extract an adversarial dataset. Then we can use this dataset to evaluate our model. So these are just two possible, we present two possible attack scenario. The first one is the classical adversarial billboard. One or double pixel billboards are used just in a single scene. And this is just a common scene-specific attack. And then we also provide an adversarial track where an adversarial patch is attached on the back of a track. And then we collected images from different scenarios of Carla at the same time. In particular, in the experimental test, we used 9 billboard scenarios among the Carla environment, and also 1 adversarial track dataset. This is just possible results that quickly, we summarize them quickly. And basically here we noticed that we tested our adversarial attacks among different weather conditions. We noticed that the attack performance resulted to not be particularly affected by the weather conditions. So also changing the specific computer vision task. And also we use this mechanism to, let's say, generate data set in order to evaluate the detection mechanism, the detection and masking mechanism, for instance, the previous approach, another one in the literature, as well also we evaluate the original model robustness. As you can see here, without discussing the numerical results that are available in the paper, I just put an illustration of the effect of ZMask using one of the adversarial patch, one of the adversarial scenarios computed on Carla. There are still open problems, let's say, to correctly, consider this work as a possible benchmark for the real world adversarial robustness. And these problems are mainly, one is the domain shift on Carla. This is because even if the Carla Town 10 is a quite photorealistic scenario, I mean, there is still a clear domain shift with respect to the real world, and we need to improve this to correctly transfer the adversarial features in the real world, but also to transfer the results that we achieve using this approach in Carla to the real evaluation of a model in the real world. And another problem is that in Carla we have a limited set of scenarios, and the last one is that we use the original model, the original metrics used to evaluate the computer vision task. However, I think that it's important to also addressing new matrices that are not available, that are not still available yet in the literature, that address the tightly phased adversarial robustness. Because just using common matrices, we notice that sometimes these matrices do not properly depict the adversarial effect of an adversarial patch. So I can conclude my presentation. These are just the main results that I think I can, for timing constraints, maybe I can skip them. Just to remark possible open challenges in future work, we would like in next work, we would like to, let's say, craft one interesting future work would be crafting less suspicious adversarial patches. Probably you notice that these adversarial patches are really suspicious from the human point of view. And we would like also to extend the scene-specific attacks to real-world scenario and also improve the transferability of photorealistic simulators. So this the previous open problem of Carl Laguerre. So this is the end of this presentation. Thank you very much. And I'm here for all the possible questions.
So thank you, Giulio. Very interesting talk, and I really appreciated the demo that you have of the detector. It's really clear and shows the effect of this detector. So I think we have a question in the chat first from Emanuele. So Emanuele asks, it's about the adversarial patches. So the first part, I think. Yes. So the goal here seems to be an untargeted attack, just for misclassifying as much as possible. Have you also considered some targeted attack scenarios? For example, it would be interesting for an attacker to mix up street pixels with car pixels to make the network think the coast is clear.
Okay. Yes, actually, and I have also an additional slide because we also test the targeted attack. I don't know if you're able to see my PowerPoint.
We see the slide, the thank you slide.
Oh, okay, let me just very quickly change. I think now you can see PowerPoint.
Yes.
Okay, so yes, this is the additional slide actually about the targeted evaluation. And yes, we, in particular in our target evaluation, the target attacks means that we switch the prediction of the attacked class. That's, for instance, a pedestrian to a target one, which could be a road or a nearest different class. And the main constraint of this attack is that we want to keep all the other pixels attached, all the other classes untouched, okay? And let's say that posing these constraints, we notice that crafting a real-world adversarial patches, it's very challenging, in particular image-agnostic attacks, so universal adversarial patches crafted in a targeted setting, resulted to be very difficult. So these are just some numerical values there. Then all the analysis is in our paper. And also, and to just reduce the constraint, we also tested image-specific patch in targeted setting. And here we can see that in this setting, the attack is, we achieve quite good results. However, there are important observations. There are, let's say, classes that are more semantically similar, like, for instance, sidewalk and road, are more susceptible to possible targeted adversarial attacks, while other classes, like, for instance, the vegetation and the pedestrian, let's say, are incompatible for possible targeted attacks. And another important, the last point is that attacking objects that are far from the adversarial patch is really hard.
Yeah, that's
yes, I have
intuitively true, but yeah, it's still
yes, exactly.
good observation. So I'm inviting. Oh, Emanuele says thanks. By the way, I'm inviting everyone to raise their hands if they have questions. Otherwise, I directly have one. That is actually, if you can expand a little bit more on the future work, like if you have some ideas on how to create, for example, less suspicious patches, maybe leveraging new technologies like the DALI models and generative models.
Yes, exactly. One of the main approach that is also, there are some works in the literature, is using generative models. However, let's say that we have also it's important to state that this model, for instance, semantic segmentation model, are quite robust to possible adversarial attacks, especially in the real world. And there are works in the literature that try to craft adversarial, let's say, not suspicious adversarial patches, but are for, let's say, for steering angle predictions that are regression, no? And let's say for semantic segmentation model, instead, we notice that using not suspicious patches, so using generative adversarial model, it's the performance, the adversarial performance is very low. And so I think that we have to take into account other possible factors that can affect the performance of the model. For instance, we can address models that have a high exploitation of the image context, as I said in the previous evaluation, or we can use poisoning to make the model less robust to less suspicious adversarial patches, for instance. As far as I'm concerned, semantic segmentation models are really robust to not suspicious adversarial patches.
Okay,
I don't know if
I yeah, that was what I wanted.
Yeah, we have to
Okay.
face several problems. I mean,
Yeah, I agree. So I don't see raised hands here. I think we have a space for one last question. So if anyone has a question, otherwise I will go ahead. Let's give them a few seconds. No raised hands. So I will go ahead with my question, and then I think it's time also to close after that. So I was wondering, because you mentioned that everything that works in the simulator, then if you move it to the real world, probably the performances are gonna be lower.
Yeah.
So I was wondering, well, first of all, this happens also with the models. If you train them with a simulator, then you transfer them to the real world, probably you see some drop. I was actually wondering if you ever tried to create a patch in the simulator and then print it in the real world, if it makes sense to do it.
Well, actually, we didn't test adversarial patches optimizing the simulated environment in the real world. However, yes, we need this model we need to retrain this model to fine tune a little bit this model in Carla, because there is a domain shift on Carla, and so we basically just update the batch normalization layer. So they are not the same models if you train the same models on Cityscape, and then you use the pre-trained model on Carla. The performance of the pre-trained model on Carla are, let's say, it has different performance, very low performance, and so I think that if you try to optimize an adversarial patch on Carla using a pre-trained model in the real world, the comparison is not fair. Okay, so you have to in some way retrain your model on Carla and then evaluate, but at the same time you are just evaluating two different models. So there are, let's say, this is a problem of transferability. You have to use a single model that is that has high performance on both Carla and Cityscape, and at that point, maybe I think it's the first step to state that this model is robust both in the real world and Carla. This is one of the main problems.
Yeah, and I think the other main problem is that when you print things, also you have constraints on the printer, because maybe they are not allowed to print every shade of color. So I think also this impacts the performances.
Yes, in the real world, we use a printability score in the loss function of the expectation of transformations. We also took into account a printability score.
Okay, so
but not in the simulated environment.
Of course, yeah. In there you have all the freedom.
Yeah, exactly.
All right, so I think it's time to close our live streaming. So thank you again, Giulio, for your presentation and for the amazing work you presented here. It's very interesting and also very cool to see these things work in the real world.
Thank you very much.
Thank you a lot. And thank you also to all the people who are participating and viewing the seminars, and see you next time. Okay, so the streaming has ended.